Alright, so I'm going to start this video by looking at Chuck Pinson's excellent book, HeathKit Test Equipment Products. There's a special section on equipment that is not normal HeathKit equipment but is still made by the same company, namely the HeathBuilt products. These were commonly sold as part of a series of equipment for educational purposes or laboratory use in universities, colleges, technical schools, and things like that. One of the arrangements that was used was the so-called Malmstott-Encke series, and another one was the Berkeley series. Both of them featured a set of laboratory equipment that each workbench in the educational institution should have for teaching the students, and while they varied in what equipment they had, by and large they all used the HeathBuilt test equipment product line, and that's what this chapter is about. So in addition to some electronic experimenter chassis, a simpler one and a more complex one, that you'd have a chassis with various parts that you could connect and do laboratory measurements and ring out the circuits and things like that, there was also the actual test equipment. I'm just going to go through it quickly, but I should point out that this series was made primarily from 1963 through about 1973, so about a 10-year period. There was a universal power supply, the voltage reference source, the transistorized power supply, the laboratory meter, which you could use to do various things with the addition of shunts and so on, an operational amplifier, actually several operational amplifiers that did not use ICs, they were done with discrete components, either transistors or vacuum tubes, and you could do experiments with those. A polarography module, a stabilizer for the operational amplifier chassis, a chart recorder, various modules that you could add on to things like the chart recorder for recording pH, or adding a log linear current module. There was a VTM, just really a version of one of HeathKit's VTVMs. There was a version of HeathKit's IO-10 400 kilohertz single trace oscilloscope, and because at the time Heathkit was owned by the Daystrom Corporation, which also owned meter manufacturer Weston, during that time period there were some products that were sold by both companies. For example, Weston had a line of volt ohm meters or multimeters that were produced by Heathkit in kit form, and also other things where Weston did a circuit design, for example, and that got turned into a Heathkit product. For example, Heathkit's first digital multimeter. But in this case, even though Heathkit had a perfectly good VOM multimeter, their model MM1, they chose to include the equivalent Weston model, which was a different design, with these different laboratory arrangements. There was a sine square wave generator, resistor substitution box, capacitor substitution box, resistor decade box, high voltage power supply, actually a couple different models, another low voltage power supply, a 15 megahertz dual trace oscilloscope, which is just a version of the Heathkit IO-105, another voltage reference source product where you could dial in very specific voltages with different knobs. You could set up each digit of the value you want and then pick different ranges or multipliers. There was a voltage to current module for that product. There was another function generator, and then a analog digital designer, kind of a glorified breadboard in a chassis, a universal digital instrument which included It was digital because the display was digital, but it included signal generators, voltmeters, multimeters, interval meters. Did I say that already? A period meter, a voltage integrator, frequency counter, all sorts of things in one instrument. Which begs the question, if you need more than one of them, do you have to buy a bunch of these? And then a pretty cool device. Heathkit sold a enlarged version of their regular VTVM, a meter face that you could hang on a wall, and then a servo meter that you'd sit on a table in front of it, and it had a big long pointer that would operate under servo control and swing the big pointer, so an instructor in front of a classroom could show meter movements that the whole class could see. There was another oscilloscope model, and yet another one, the so-called high gain oscilloscope, and that's pretty much everything in that series of equipment. So this video is going to be about the EUW-17, a transistorized power supply, also made in that 1963 to 1973 time period. It isn't a regulated power supply. It's really just a rectifier and a filter capacitor with a transistor used as a amplifier to the capacitance. So it acts as if it were a rectifier, filter capacitor power supply with a much larger filter capacitor than the one that's actually in it. But it doesn't actually regulate the voltage, it just filters it really well. And then I'll also be talking about the EUW-16, which is a voltage reference source. So going back to the EUW-17, and I should point out that the EU is the prefix for this entire series no matter what device it is. Elsewhere in Heathkit's product lineup, the first two digits or the first two letters told you what type of equipment it was. Here everything is the EU series, and the W refers to the fact that it's factory assembled and wired. Not everything in the series has the W, especially if building it is part of the educational process, but the vast majority of the products in this series are EUW types. So the output voltage on the EUW-17, it's output voltage unregulated, 0 to 25 volts at maximum current, or 0 to 35 volts under no load. Right there, that shows you it's not a regulated supply. Let's see, ripple less than 0.1% at full load. It's a full wave rectifier. Heathkit replaced this with the IP-18, an actual Heathkit product, which I also have a video on. Uses one transistor and a couple of silicon diodes. Alright, let's get into the actual product now. Okay, here's the artifact. Just a simple box. Heathkit used similar style boxes on lots of their products, and it certainly got used on many of these HeathBuilt products. There's the logo. Looks just like Heathkit, except it has the word built instead of kit. All of the products in this series had the same kind of off-white chassis or outer case, and then the front panel and the rest of the sheet metal would have this weird green color. I always say it looks like the color that the Russian or Soviet Union aerospace industry used for the color on the inside of their airplane cockpits. I've seen that color a lot. Actually, some Douglas aircraft built in the US had a similar color for their cockpits. It's not actually a bad color for that type of thing. It's not too light, it's not too dark, it's a pleasant color. Anyway, so it has Heathkit-like characteristics and un-Heathkit-like characteristics. One thing is the power switch. Heathkit never used a power switch like this. They always used simpler black slide switches. This one has this red switch, and a lot of products in this series have red power switches. The knob is just a regular Heathkit knob. I don't think they had anything special for this. Around the back, something else you don't usually see on Heathkit products. An external fuse in an actual fuse holder. Most of these, most of Heathkit's products either had no fuse if they were earlier ones, or you would have to open up the case. There's my air compressor going downstairs, sorry about that. Most Heathkit products you'd have to open up the case to change the fuse. On here, probably because it was, you know, for a less hobbyist oriented customer base, they put on proper fuse holders on the outside. And I think that's consistent across the product line. There's a little plug in here, which I wouldn't be surprised if that turns out to be something that can be removed for access to a potentiometer inside, maybe. We'll find out. I have removed the screws on these. This is another thing that's a little different from the way Heathkit did similar style cases. They still had screws usually on the bottom and the sides, but on these, the screws going in up here are going into speed nuts instead of just folded over flanges on this part of the case. Another thing that's very different from Heathkit, Heathkit test equipment pretty much universally used stick-on rubber feet, where on here they're riveted on plastic feet. So more durability, takes more abuse probably. Now let's pop it open since I've taken the screws out. Here's what I was talking about before. If this was a Heathkit product, it would probably just have this edge with a flange folded over and then the speed nut stuck on it. But here they have an actual aluminum bracket that goes all the way across and has flanges for the speed nuts. It's just a little nicer way of doing it. These probably cost more than the Heathkits, and at the same time that same piece of metal is used as a chassis for other things. So we have the power switch here, and here's something which is really a honker. Look at that. This is the AC line coming through here, and it's just, you know, well, as Dave Jones would say, a bee's dick away from the metal chassis. That's bad design. It's just like waiting for a breakdown to occur there. Otherwise, it has a power transformer inside. There's the inside of that fuse holder. There's a terminal strip there. There's the one potentiometer down inside. It turns out this is not something that can be taken out. It's just a rivet to hold the clamp that holds this capacitor in place. Heathkit would have used a screw there, almost certainly. But here they're using a rivet. So again, just a little different from their normal way of doing things at Heathkit. Plus they're using one that has anti-rotation pins on it. The capacitor clamps Heathkit used on their products of this same era did not usually have that. They could twist around if the screw got loose. Let's see what else. So, a regular neon bulb for power indication, and a couple of resistors, not much in there. And I know I'll find it if I keep looking. Oh yeah, way down, there it is, right in the middle of the picture. There's a transistor in a heatsink that's also mounted to that inner aluminum chassis. And I should find some diodes here somewhere. I can figure out where they're at. Oh yeah, they're back on the back side of this terminal strip, almost hidden from view. So I imagine we'll find two diodes in there forming the full wave rectifier, and that would mean that the transformer would be a center tap most likely for that to work out as a full wave rectifier. And there are two large filter capacitors, electrolytics. They're really old, to the point where I'm sure they're bad. They need to be replaced. I've got some new ones on order. At least on here it's reasonably accessible. I don't have to completely discombobulate this, I don't think, to replace those caps. And hopefully nothing else will be bad in it, so it should just fire up once I do that. I bought this from a eBay seller along with the other two HeathBuilt things I have in this video series. eBay seller in Beaverton, Oregon, which, as many viewers know, is one of the hotbeds of American high technology, companies like Tektronix being based there, for example. I wouldn't be surprised if these were used in a local college or technical school, or maybe even on the laboratory of some high-tech company there for some reason, or maybe that company even had a little training lab or something, and they were probably reasonably well taken care of by professional people. And I don't know the history of this, but the seller said that they came out of a laboratory that was still in working order, so it should work just the way it is, but I definitely don't trust those capacitors, so we'll replace those. Alright, I put in new capacitors, electrolytics. They're 470 microfarads instead of the original 500, but that's close enough. And they're the same voltage, 50 volts. And because the leads are really hard to get at for unsoldering, I just decided to keep the original very thick leads. They're almost like bus bar, right up close to the capacitors, and then make the new capacitors just go and wrap around and solder onto the thick bus bar like leads of the original. On this one I had to insulate because they pass over this metal bracket, so I slipped some heat shrink over them, but basically did the same thing. I took a little piece of Mylar, bent it, and super glued it to the aluminum bracket there so that it provides some insulation in case one of these wires gets too close. Now I'm going to squirt a little deoxit into the pot and the power switch, and it should be ready to test. Well, I did a preliminary test of this, and it was working and it was adjusting the voltage properly, but there was a little pulse, like once a cycle there was a little thing like that would appear, just a little nub with a little shoulder on it like that. So this was happening once every 60th of a second, and I really couldn't see a reason why it would be doing that with the design, but I happened to look at the schematic that I got offline, and it shows a 3300 ohm resistor and a 0.1 microfarad capacitor across the output, and in the description it says the 3300 ohm resistor acts as a bleeder and also applies operating current to the transistor under no load conditions. The 0.1 microfarad cap filters out any noise pulses present in the power supply. And I thought, maybe this is a problem they discovered with this and retrofitted that on, because it doesn't appear to be part of this. I don't see any other capacitors in there. The diodes are pretty clearly doing their job, although maybe one of them is bad. I could probably try replacing the diodes, but I don't think that's the cause of it. It certainly doesn't have that resistor, and it certainly doesn't have the capacitor. So I might try putting those on there to bring this thing up to current standards, if you will. The problem is it's really hard to work on chassis of this style. It's so full of parts, it's like, how do you even get in there to do it, really a pain in the butt. But I do have a couple of suitable parts in the correct values, so I'm going to see about putting those in there. Well, I put the fix in there. It's really hard to see, but there's the capacitor and the resistor way down there by there's a better view of it, just tacked right across the terminals. So a quick check here. I've got my scope set up, and turn this guy on. I'm down at minimum voltage, and I'm going to turn the knob up. Nice and smooth. Does not have that glitch in it anymore. That apparently was the trick. If you just put a voltmeter across this, you won't notice those little glitches. it just looked very unclean to me, and apparently Heathkit agreed, and I believe that these two components there were their solution to that problem, because it definitely makes the difference on this one. Alright, now I'm going to complete my restoration. As far as restoration goes, besides what I've already depicted in this video, I just went over the outside of the case with isopropyl alcohol and quite a lot of rubbing, tried to get it as cleaned up as possible. There was a pen mark on here that I really had trouble getting rid of, and I finally resorted to using a little bit of acetone on the end of a Q-tip and had to rub it for about, I don't know, 60 seconds, about a minute, before it almost went away. It's still slightly visible, but it's not the really big blemish it was before. And I went over the grooves and the knobs and the knurls with the tip of a really small jeweler's file and isopropyl alcohol and a lint-free wipe, and cleaned the crud out of the slots there. And that's about it. And I changed the corroded screws on the sides with 632 black anodized button head screws, and I replaced the corroded zinc plated screws on the bottom with modern ones of the same type and size. Alright, I'm going to wring this guy out a little bit. It's supposed to be able to supply at least 0 to 25 volts at up to 200 milliamps maximum. It's not a voltage regulated power supply, so I would expect to see some voltage sag as the current is increased, but we're going to see if the waveform stays reasonably stable. So I've got it plugged into my AC power source over there. I'm going to turn it on, and on the scope I'm seeing a trace with 0 volts, and the electronic load is reporting 0 volts as well. Well, 0.028 volts anyway. I've currently got it set for 1 milliamp, so I'm going to turn the load on, and we're showing essentially 0 volts there. I'm going to turn the supply up and try to get it around 5 volts. There, about 0.5. Alright, scope is showing a pretty nice flat waveform. Power supply is showing 4.99 volts. And I'm going to increase the voltage all the way up until it doesn't go anymore. And it's going to 32 volts and a half, which I think the scope agrees with. 5, 10, 15, 20, 25, 30, yeah, 35 volts, thereabouts. It's reading a little different, but on the other hand, well, no, I don't know about that. I'll take it down to about half of its rated voltage, and there's quite a lot of capacitive lag on this, so after you make an adjustment you have to wait just a moment for it to catch up. So I'm going to set it for roughly 15 volts, get as close as I can. 15.1 volts. And now I'm going to increase the current. I've got the cursor under the current, so I'm going to crank that up to 10 milliamps, and it did sag as I expected it would. Still no ripple on the power supply that I can easily see. Go up to about 50 milliamps. Yep, so 50 milliamps, it's dropped to 13 volts. This is because it's not a regulated power supply. Output is still clean though. I'm just going to crank it up to the highest rated current. Well, I'm going to go to 100 milliamps first. Drops to 12 volts. Now I'm curious to see at this current if I can still get well more than 25 volts on there. So I'm going to set it for 25 volts here and increase the current up to 200 milliamps, and the output can be increased to 26. So yeah, so I'm going to take that back down, and at about 18 volts it's still a clean output, so it's doing its job, but it is not regulating the voltage. Turn the load off, and now I go back to 32 volts with no load on it. So it's a power source, and it'll probably hold a nice smooth DC output, but it will not regulate the voltage as the load changes. For that you need feedback, and this circuit does not have feedback. Okay, there's the beauty shot. I was not able to find a complete manual for this online or from any of the usual manual sellers, but I was able to find 2 pages, the specification sheet and the circuit description and schematic diagram sheet. So let's just go through that to be thorough. I use my dirty Q-tip as a pointer. This unit is not a regulated power supply. It was designed as a low voltage power source with good filtering and variable output voltage. Since the output resistance is quite low, small changes in load current do not significantly affect the power supply voltage, but of course big changes do. Output voltage is 0 to 25 volts at maximum current, 0 to 35 volts with no current output, so that matches what I was able to see with my instrumentation. Output resistance less than 50 ohms. Ripple less than 0.1% at full load, and that was certainly borne out with my oscilloscope test. No visible ripple even when I cranked the gain up quite a bit. Semiconductors, 2 silicon diodes, doesn't say what kind, but at this low current they could be anything. Probably I would replace them with a 1N4004 or something like that, or even a 4001 would probably be adequate. An R265A, that's a Texas Instruments part. It's a PNP power transistor. Not a very high power transistor, but a power transistor nonetheless. Circuit type full wave rectifier, not a bridge, but a full wave rectifier. Controls, as we already know, a voltage knob and an on-off slide switch. Power requirements, 105 to 125 volts AC, 50-60 hertz, uses about 9 watts. Weight 1 3/4 pounds. Alright, let's take a look at the other sheet. There's the schematic again. So, the usual thing with a line cord and a power switch, a neon pilot lamp with a current limiting resistor, and the primary of the transformer. Now I'd thought that the fuse on the back was for the primary circuit, but as it turns out, it's in the output circuit to protect the semiconductor. So again, the thinking back in this period of time with Heathkit is, fuse what fuse? They just didn't put them on their older stuff. I think they started wising up in the 80s and putting fuses in. So the output is a center tap secondary, 25 volts AC on either side of the center tap. And then there's a diode on each outer end of the winding, tied together. And between that and the center tap, that gets you your full wave rectification without using a bridge. Now because it's a PNP transistor, everything's kind of upside down from you might otherwise from how you might otherwise see it. So the center tap of the transformer that would usually go to circuit ground or something on a regular power supply here just goes to the series pass transistor, and through that to the negative output terminal, or the minus output terminal, through the fuse, of course. And then the positive side of the rectifier goes straight out to the positive output terminal. So again, with a NPN transistor, the whole circuit here would be flipped upside down, so the transistor is up here on the positive leg of the supply, and the negative leg would just go straight back to the center tap. But it's a PNP, so everything has to be flipped upside down. But it works the same way. Now, I don't know. I redrew it, even though it's very simple. Very small changes in the way things are shown, but I showed them anyway in my sketch. So you come out of the rectifier, you have a 500 microfarad capacitor for rough filtering, and across that is a 5K potentiometer, and that's the front panel voltage control. So you pick off a voltage between whatever the voltage is up here and circuit common, and that goes through a 470 ohm resistor and then is filtered. So because the common of this circuit is the plus side, the filter capacitor goes to the common, and of course the plus side is towards the highest voltage, so that's correct. So you end up with a filtered voltage off of the trim pot, and that is used to control the transistor. 22 ohm resistor, really small value on the base. With a silicon transistor, there's going to be a roughly 0.6 to 0.7 volt drop from the emitter to the base. So whatever voltage you put here, it's going to try to keep the output at that voltage minus the 0.6 or 0.7 volts. But without feedback to adjust the base voltage, it's not able to hold that voltage. As you draw more and more current through it, remember that this transistor is really just acting as a resistor. So as the resistance out here gets to be less, therefore more current is being drawn, compared to this resistance, it's just going to change the voltage, because it's just a voltage divider between the power source here, the resistance of this transistor, and the resistor that's out here on the load. And being a simple voltage divider, it can't help but have its voltage change somewhat as the current changes, just Ohm's law. So in a regulated power supply, you would tap off the output voltage and feed that back through a circuit that would adjust the base voltage as required to keep the output voltage where you want it. This obviously doesn't have that. And then again, we have the protection fuse that's there to protect the transistor, probably. And it'll protect everything in this circuit, but primarily the transistor, I believe. And then obviously Heathkit did not originally have this load resistor across the output, which they say is again there to act as a bleeder to draw down the voltages on the capacitors when you turn it off, and also to provide a minimum operating current. So this is, I don't know, more stable, just works better, better. And then they obviously found out that with this scheme you were getting a little bit of ripple that was still getting through to the output, and they could solve that by putting a 0.1 microfarad capacitor across the output, and that certainly worked, because that ripple went away on mine once I added that capacitor. So if you have one of these things and you have never looked at the output with a scope, I suggest you do it. And if you've got that little ripple on there, halfway ripple, then you think about adding this fix, add these two components that were clearly not there on the earlier production models of this product. But that's all there is to the circuit.